Hi, Sammie. This is 17.111. Notice I'm using the numbers from the book. I don't have the numbers that you gave me anymore. But the problem is the same, except for those numbers. They want the pH, and they want the concentrations of all the ions. All the ions. There are going to be a whole bunch of ions here, because when you put this in the water, it will dissociate into this. Why? Because anything with potassium on it or sodium on it will dissociate completely. So this dissociation shows that if I have two of these and one of these for every one of these, then one of these ions is going to be K. Okay? And if I have 0.33 molar of this, then I'm going to have double that for K. That makes sense, right? Oops. Okay, so we're already starting off with one of the answers there. It's K plus, sorry about that. Now, if there's 0.33 molar of this, that means there's also going to be 0.33 molar of this, right? So let's see what happens when you have 0.33 molar of this. This carbonate ion is a weak base. So, because it's a weak base, I'll do an ice chart for it. In slide 81 and slide 82 of the lecture notes that you gave me, Sammie, the professor does this type of problem, but for the acidic side. But what is this? HCO3. As I examined this 17.111 more closely, I realized that it starts with a weak base rather than a weak acid, so it's best to approach the problem as a base problem, with Kb rather than Ka. So this this equation is the base equation for this weak base. This water, it's HOH, so that OH goes there, and the H goes on that CO3 2 minus, creating an HCO3 1 minus. It's 1 minus because this H was H plus. That H is H plus because the OH is OH minus. But you knew that. Okay, so what is the Kb for CO3 2 minus as a weak base? You could look it up someplace in your book, but I looked it up someplace online, and I found it over here. Not that one, that's the hydrogen carbonate ion. Here it is, carbonate ion, right here. It's 2.1 times 10 to the minus 4. Okay, so this is 2.1 times 10 to the minus 4. I'm going to write that as 0.00021. And that's equal to the OH minus times the HCO3 minus. That there, HCO3 is the bicarbonate ion, also known as the hydrogen carbonate ion. The minus sign should be inside these brackets, not outside. Okay, so we're starting with 0.33 molar. That's what's given to us in this problem from the book. And there's none of this and none of this because all they said was 0.33 molar of that potassium carbonate, and they didn't say that there was a pH or anything yet. They were asking for the pH. So what's the change? With those zeros on the product side, the change is going to be minus x here, plus x, and here we will have this, this, and this. So this Kb this Kb expression is going to end up meaning that there's an x here, and a 0.33 minus x over there. So x squared over 0.33 minus x. Now on slides 81 and 82, your professor ignores the minus x here because the Ka that your professor was working with in his Ka acid problem, the Ka was less than 10 to the minus 5. But here, I'd rather not do that because the Kb is more than 10 to the minus 5. It's something times 10 to the minus 4. Now, as it turns out, the difference is only 0.01. I mean, we'll see in a moment here that x is such that 0.33 minus x equals 0.32. So in your class, Sammie, it might be perfectly fine to still ignore the minus x here and just call this 0.33. But for now, I won't do that. I'm going to work through this. I'm going to solve the quadratic equation with it. Give you a new page here. Okay, there's the new page. I'm doing 0.00021 equals x squared over 0.33 minus x. So that's 0.00021 times 0.33 minus x equals x squared. And that means, get the calculator out, 0.00021 times 0.33, that's 0.0000693. 0.0000693 minus 0.00021x equals x squared. Okay, 0. I'm assuming that you are not going to be using your calculator and working through this on your own because this is not your problem. This is just a problem similar to your problem where the numbers are changed and you're just watching to see how this problem is done. You would use your graphing calculator, of course, because you have one to do this. I don't have one, sorry. So I'm using a website. Oh, do you want to see the website that I'm using? Just in case you want to see it, that's the website that I'm using. So 1 was the A. Let's see. So that was the A. Here's the B. 0.00021. So I got 0.00021. And this was it negative? Yes. It's negative 0.0000693. Okay, so the answer here, I get a negative answer and a positive answer. Of course, in chemistry, we're only interested in the positive answer, 0.00822. So x is equal to 0.00822, and that's going to be molar. Excuse me. Why is it molar? It's molar because we were doing the ice chart here. We're doing the ice chart, remember? So this is 0.00822 molar. This is 0.00822 molar. And this is 0.33 minus 0.00822 molar, which ends up being roughly equal to 0.32 molar. Okay, so now we have an OH. So from here we could calculate the POH and then thereby get the pH. We also have an HCO3 minus concentration. So this is one of the ions. See, one of the ions that they were asking for. We already have one, K+, and now we have another one, HCO3 minus. And we also have CO3 2 minus over here. So we're going to have CO3 2 minus over here. And of course, we'll have OH minus, and we'll have H3O plus, just because there will be a pH. You know, when there's a pH, there's going to be OH minus, there's going to be H3O plus. Oh, and here is the OH minus method. So can we fill in these answers? No, we can't. And the reason why we can't fill in these answers yet is because this thing here is itself a weak base. So we need to do another ice chart. Now that this has formed, does that make sense? We have formed a new weak base, so this new weak base will do this business by itself too. So that will change, or that might change, the OH minus concentration, and it will change the HCO3 plus concentration, because this will break down to break up water into OH minus. Let's do that. Here's your new page. Here's your HCO3 minus, doing its base thing with the water. And what does this become? Well, water is HOH, so the OH minus comes off there, and the H plus hits that, so you get H2CO3. That's carbonic acid, and I believe they mentioned carbonic acid in the problem. So that is a hint that we are on the right track. That there is carbonic acid. Okay. Ice chart. Just a matter of interest to you as an athlete, that carbonic acid and this bicarbonate ion, this is the buffer system in your blood, you know, because carbonic acid and bicarbonate ion, you know, they're related to carbon dioxide gas. Okay, so there's none of this. Okay, oops, there's 0. So this is the change is going to be minus x, and the reason why we know that is because this is 0 here. So because there's a 0 on the product side, it means the reaction is going to go to the right, as you know. Okay, so what's the KB here? This is a new base equation. It's the base equation of hydrogen carbonate, or the bicarbonate ion. So I'll go in the book or online to find the KB. I went online. And here's the KB. Whoop. That's not it. Whoop. There it is. So it's the hydrogen carbonate ion, or bicarbonate. The KB is 2.4 times 10 to the minus 8 there. 2.4 times 10 to the minus 8. That's convenient. Why is that convenient? It's convenient because 10 to the minus 8 is a lot less than 10 to the minus 5. So that means I'm allowed now to ignore the minus x. Actually, it might be beneficial not to ignore the minus x for me, but for you, you would definitely be allowed to ignore the minus x. But, you know, I'm just looking at this being 0.00822. This number is already pretty small. So maybe the minus x might turn it into a 0.00821 or something. I'll just try it. I'm pretty sure that you wouldn't have to try it, but let's see. So my equilibrium expression. Oh, sorry. Just to be complete here, right? Okay. So this is 0.00822 plus x. This is x. This is 0.00822 minus x. Okay. So if you, Sammie, were to ignore this minus x, then you would also ignore this plus x. Okay? So this this math problem would be much simpler for you. But let me just verify that that's the case. But it would be okay to ignore those things, because I'm not sure. The reason I'm not sure being this number is so small already. Okay. Now I need a new page to get some more room. So the number was 2.4 times 10 to the minus 8. The numbers up here were 0.00822 plus x times x over 0.00822 minus x. So I cross multiply and I get 2.4 times 10 to the minus 8 times 0.00822 minus x equals, and I distribute this, equals 0.00822x plus x squared. Okay. Calculator. Zoop. 2.4 to the power of 10 to the minus 8 times 1.9 times 10 to the minus 10. 1.97. Okay. 1.97 times 10 to the minus 10 minus 2.4 times 10 to the minus 8x equals 0.00822x plus x squared. You like my little song, Sammie? Okay. 0 equals x squared plus 0.00822x plus, I'm bringing this one over to the other side, 2.4 times 10 to the minus 8x. I'm bringing that one to the other side, minus 1.97 times 10 to the minus 10. 0 equals, I'm going to combine this x and this x. X squared plus 0.00822x. Okay, now notice that 0.00822 is 8.22 times 10 to the minus 3. That means this 2 is in the 10 to the minus 4 position, this 2 is in the 10 to the minus 5 position, and that means 10 to the minus 8 is not even going to touch it. So that's negligible. Minus 1.97 times 10 to the minus 10. Okay, that's my quadratic equation. I go to my equation solver. Okay, here I have the b, it's 0.00822. The b, okay, the b was 0.0082, oops, 822. Okay, and the c, where is the c? Here's the c. Negative 1.97 times 10 to the minus 10. So the c was negative 1.97 10 to the minus 10. Oops, 10 to the minus 10. Okay. So the answer is the positive one. 2.4 times 10 to the minus 8. Okay. X equals 2.4 times 10 to the minus 8. Alright. So, let's go into the other page. Okay. Do this in red. Okay, X was 2.4 times 10 to the minus 8. And look, I see this is 8 times 10 to the minus 3. So the 2 is in the minus 4 position. The other 2 is 10 to the minus 5 position, so it's not even going to get touched. So my conclusion here is that you don't need to worry about this. You don't need to worry about this. So when you do this problem, Sammie, for whatever number they gave you in this problem, you do not need to worry about the minus x with the plus x. Your problem will look like this. 2.4 times 10 to the minus 8 equals 0.00822x over 0.00822. There will not be an x squared even in your problem. Okay, Sammie? Because I have just seen here, and you have watched me seeing it, that the x is so tiny it will not even matter to the 0.00822. Okay? In fact, it really shouldn't even be 0.00822. It should be just 0.0082. And that's because this is a 2 significant figure problem. And it's a 2 significant figure problem because they started me out with 0.33 molar, not 0.330 molar. And they started you out, I remember, with some other number that was also 2 significant figures. Moreover, the KBs that I'm getting are also 2 significant figures. So this is a 2 significant figure problem. So anyways, this number here is 2.4 times 10 to the minus 8. Okay. Interesting, isn't it, that the KB is in fact the same as x in this problem? Very interesting. It's almost as though we didn't have to do all that math. But that's beyond me for right now. So, now I have the answers. This is the concentration of H2CO3. This is the concentration, not this. This is the concentration of OH minus. This is the concentration of HCO3 minus. Okay? Does this make sense to me? If it doesn't make sense, send me email. Tell me where it doesn't make sense, and I'll answer your email, and then it will make sense. Okay? Where's my, okay, here it is. So, let me clean this up a little bit. Okay, so we need the brush. We need the pH. So we already know that the OH minus concentration is 0.0082 molar. We already know from the beginning of the problem that the K plus concentration was 0.66 molar. But unfortunately, I erased that just now to clean up the board here. And we know now that the CO3 2 minus concentration is in fact, where's that page? Not that page. Not that page. Yes, this page. This, it's 0.32 molar from our first ice chart, remember. That didn't change. Our second ice chart did not change the CO3 2 minus concentration. Nothing changed the CO3 2 minus concentration except for the first ice chart. The reason for that is CO3 2 minus didn't even show up in our second ice chart. I'm looking for the second ice chart for you. There it is. No, that's not it. There it is. This is our second ice chart. Notice there is no CO3 2 minus here. Okay? So back to the first ice chart. CO3 2 minus concentration is 0.32 molar. Back to the start page. 0.32 molar. Okay? And then, I'm not sure if they asked for the carbonic acid concentration. Just in case they did, remember that showed up on our second ice chart, which is here. No, that's the first ice chart, which is here. No. Oh, drat. Where is the second ice chart? Is it the black one? No. Sorry. It's this one. Okay, good. The black and red one. So, there it is. H2CO3 carbonic acid, 2.4 times 10 to the minus 8. And where's our start page? Here it is. So that's 2.4 times 10 to the minus 8 molar. Okay. And there was, of course, HCO3 minus, whose concentration was 0.0082 molar. Okay. Now let's find the pH. At this point, you are allowed to stop the video because you know how to calculate the pH. So you have all the information you need to tackle your version of this problem. But just to be complete, while you do whatever it is that you do, I'll be doing this. Bye, Sammie. You know, you've been a great audience. Calculator! Negative 2.09. $11.91. It's important to have two digits after the decimal point, in case you're still watching here. Sammie. The reason is, when you do a log, the significant figures rules change. I'm not sure what they are, but I suspect they are the number of digits after the dot. I don't think the digits before the dot, even though they're not zero, count for significant figures after you do the log. But I'm not sure about that. But anyways, that's the pH. So these are my results for this problem. Yes, finally finished it. Yay! Now I can do whatever I want to do. Bye, Sammie. Have a good weekend.